So now it's a very great pleasure to have John Mather give us a talk on Hamiltonian dynamics.
Thank you. So I thank the organizers also for inviting me and for supplying the title for my talk also. This is the first time that I've had this title supplied in my talk. And it's a very broad title, which permits me to talk about lots of different things. But I only have an hour, so I won't talk about so many things. And anyway, there's plenty I don't know about Hamiltonian dynamics. So, well, in G.D. Birkhoff's book on dynamical systems, he conjectured that, you can, in the Newtonian n-body problem, I suppose everybody knows what the Newtonian n-body problem is. It's n-point masses acting under the influence of Newtonian gravitation. So you have n positive masses, and they act under the influence of Newtonian gravitation. And one question, well, you can discuss orbits which are bounded or unbounded. This means simply that the distance between the particles either stays bounded for all time or... Oh, okay. I'm sorry. Okay. So I was saying that Birkhoff, in his book on dynamical systems, posed a problem about the n-body problem. So you can talk about, in the n-body problem, you can talk about bounded orbits or unbounded orbits. Unbounded orbits meaning that bounded orbits meaning that the distance between between any two particles remains bounded for all time, and unbounded being the other orbits. And he conjectured that the unbounded orbits are dense in the phase space. So for any initial condition, meaning position and velocity, you can arbitrarily well approximate it by something which an initial condition such that the orbit starting at that initial condition becomes unbounded eventually. I mean, as t goes to infinity, the distances either go to infinity or oscillate. Presumably, you could conjecture even that they go to infinity for a dense set of initial conditions. And this seems like an incredibly hard problem, which nobody's made the least bit of progress on, except one version of it, in which this was proved to be false in the 60s by Jürgen Moser. Let me just mention that version of it. This is the so-called restricted three-body problem. So let me say what the restricted three-body problem is. Well, the restricted three-body problem is a two-body problem where the two bodies go in circular orbits about each other. So that's simple enough. And then there's a third body, which acts under the influence, which moves under the influence of the first two bodies. And it certainly seems from reading Birkhoff that he thought that the restricted three-body problem also had a dense set of initial conditions whose orbits became unbounded. But this, I don't think he ever said it explicitly, but this was proved to be false. This is part of the so-called KAM theory, which is surely the most basic results in Hamiltonian dynamics. This is Kolmogorov, Arnold, and Moser. Now, Moser, they obtained all sorts of results, but let me just mention one result which is due to Moser, was worked out explicitly by Moser, which is that in the restricted three-body problem, there's an open set of initial conditions for which orbits remain bounded for all time. So in the, let me say, in the circular meaning that these two bodies go around each other in circles, planar, the third body is in the same plane as the two bodies which go around in circle. Restricted three-body problem. There's an open set of initial conditions for which all orbits remain bounded. Okay, so, well, probably many of you are familiar with this result, but since this is supposed to be an expository lecture, and let me say something about how this is obtained. What's special about the restricted three-body problem is that it's what's called a Hamiltonian system in 2 degrees of freedom. Well, you have 2 degrees of freedom. There are two possible the possible positions of the third particle are in the plane, and so that means 2 degrees of freedom. There are also, for the initial conditions, there are two velocities also. So the phase space, see, usually you reduce the system of differential equations to a first-order system of differential equations just for convenience. So then you have to introduce the velocities also into your phase space so that you have a first-order differential equation on the phase space. So the positions and the velocities form a four-dimensional manifold, but the positions alone form a two-dimensional manifold. And so for that reason, the system is said to have 2 degrees of freedom. Now, what the basic thing that KAM theory has to do with is the so-called persistence of invariant tori. Now, so the basic result is that if you have, let me state it this way. It's not quite accurate, but it's close enough for my purposes. So, if you have a Hamiltonian system in n degrees of freedom, so you have n degrees of freedom, which means you have a 2n dimensional manifold. The number of dimensions of the phase space is twice the number of degrees of freedom. Well, it's a Hamiltonian system, so this means that you have a symplectic form, omega. So that's a symplectic form is a non-degenerate 2 form which is closed. And you have a function h, which is the Hamiltonian function, which defines the system. The system is defined as the symplectic gradient of h. So you have a vector field xh equals the symplectic gradient of h. Well, a symplectic gradient is formally like a gradient, but it's related to the non-degenerate 2 form formally in the same way that a gradient is related to a Riemannian metric. So if you have a Riemannian metric has a gradient, if you have a symplectic structure, it has a symplectic gradient, which is well, it's defined by omega of xh comma y if y is a second vector field equals dh of y. So that's what's called the symplectic gradient. Now, what the Kolmogorov-Arnold-Moser theory concerns is an invariant torus. So you have a torus in your phase space, n-dimensional torus, which satisfies a number of conditions. I'm going to run out of room here, so let me. So now you have a torus in the phase space, and it's invariant. So invariant means that xh is tangent to Tn. And in fact, you assume that xh is linearizable on n. So assume xh is linearizable on n on Tn.
Time variables that are into this.
So linearizable, I mean that so I can find a coordinate transformation of Tn to itself, which changes this to a linear vector field. And then the time variable comes from integrating the vector field.
So, I mean, you have a driven system, or do you choose rotating coordinates?
No, xh is xh is the system. Xh is the vector field. So xh defines the system. The system's defined by, if I call a point x contained in M, then it's dx dt equals, maybe I was making this overly abstract.
Yes, but that particular system, unless you put yourself in a rotating coordinate system, the force will depend explicitly on time. You put yourself in a rotating vector field.
Yes, that's right. That's right. Oh, I see. I'm sorry. I didn't understand your question. So you're asking about this. Yes. To make this one a system of 2 degrees of freedom, you put yourself in a rotating coordinate system. I mean, to make it time-independent. Sorry, time-independent system of 2 degrees of freedom. So, okay, so they start with this torus, and xh is linearizable on it. Let's call it xh0. So I start with an unperturbed system. The KAM theory has to do with small perturbations, so I'll start with an unperturbed system, x0. Let's see. I assume it's linearizable, and I assume that it has a dense orbit. And not only is it dense, but it comes back. It comes close to every point with a certain frequency. It doesn't take a tremendously long time to get to every point. This is what's called a Diaphonic condition. I won't write down explicitly what the Diaphonic condition is, but I'll assume a Diaphonic condition. So that says basically that the flow on this torus not only is linearizable, but it and dense, but not only is it dense, but it comes, if you take an arbitrary pair of points, then the orbit starting at this point, and you take a neighborhood of the second point, then an orbit starting at this point comes within this neighborhood, the other point, within a certain time, which grows polynomially with the inverse size of this neighborhood. So that's what's called a Diaphonic condition. Now, and then they prove that let H be a small perturbation. I think now there are these experts like Michel Herman who are interested in the best estimates. They've gotten it down to something like a Cn+2 topology. Well, I'm sorry, I haven't given enough conditions. There's also a normal condition. I'm not going to say what it is. There's a normal condition. Condition on the on what happens on the normal space to Tn and M2n. So let me. It's a non-degeneracy type condition. Let me just. For the experts, it's called the Kolmogorov condition. On the throw induced on the normal bundle, so what they say is let H be a small perturbation in a Cn+2 topology. Then near the original invariant torus for xh0, there exists a new invariant torus, a perturbed invariant torus, for xh. So in the case, so as was pointed out, I need to introduce a rotating coordinate system. Then I get a time-independent system, and I get a system in 2 degrees of freedom. In the system of 2 degrees of freedom, since this is time-independent, you have a 2-dimensional torus in M4, and then you have an energy surface. Well, you have conservation of energy, so this is preserved. So the family of such tori divide the 4-dimensional any such 3-dimensional torus separates the 4-dimensional manifold into 2 parts. Sorry, a 2-dimensional manifold, any one of these tori separate the 4-dimensional manifold. Sorry, a 2-dimensional torus separates this 3-dimensional manifold into 2 parts. So to go back to this system, well, you can you can look at this as a perturbation of a system where you just have one particle at the origin with the rotating coordinate system. If you introduce the rotating coordinate system, actually you get, see, if you do it without the rotating coordinate system, you just have circular orbits. But if you introduce the rotating coordinate system, the orbits become irrational. You get 2 irrationally independent frequencies, and you can view it as a perturbation in this way. And so you get these tori which are preserved, and you get this. So you get tori which are near the circular orbits, and this divides the phase space. This divides the phase space into various pieces, and these remain in these open pieces and stay there for all time. So this is a very classical result, which any expert in Hamiltonian systems would know. Now, one can, of course, vary this problem in many ways. So I'd like to mention one way. What I want to discuss is a system where I replace the 2 orbits going about each other, 2 bodies going about each other in circular orbits with 2 bodies going about each other in an elliptical orbit. So let's replace this with a circular.
John, I missed where your unperturbed torus was for this problem.
You take the two particles at the same point. Now you have a rotating coordinates. Now this would give you a one-dimensional torus, you think, but you have a rotating coordinate system, and it rotates at a different frequency from the. That's. Yeah, it's integrable. It's integrable, but you need a two-dimensional torus. You need enough degeneracy to apply the. Actually, to apply the KAM theory to the n-body problem is a real mess because you don't have the non-degeneracy. You don't have the Kolmogorov condition. Arnold wrote a long paper applying it to this case, which I never understood the paper. It seems very difficult, but. No, I'm rotating these two. I'm rotating these two. So the coordinates are arranged to fix these two, the ones with positive mass. So you look in rotating coordinate systems so that the two ones with positive mass stay fixed. And
You're starting with these two masses coincide?
well, then I replace the two masses by a mass at the origin, and I keep it rotating the same speed. I don't make it rotate infinitely, but
Particles approach each other, the speed has to go with energy.
right. But I don't change it in that way. I just keep it rotating the same speed. I mean, this is just a mathematical artifact. I don't have to. You see, the point is that you could imagine one particle at the origin, and then you know what the dynamics is, and then you can do the same dynamics but with a rotating coordinate system. It's exactly the same dynamics, you just change the coordinates. So you can rotate it however fast you want. So to view this as a small perturbation of an integrable system, I rotate it at the same speed that these two are rotating.
You've got an energy surface, so it becomes three-dimensional, and then the torus is...
It's two-dimensional.
What?
It's two-dimensional.
What's two-dimensional?
The torus. Yeah.
You've got a three-dimensional energy surface?
That's right, yes. Sorry, I was completing your sentence. So that's why KAM theory gives such a result. Now, in more degrees of freedom, or with more particles, it gives you tori, but it doesn't give you tori which separate, because I mean, this is very special for n equals 2. A two-dimensional thing separates a three-dimensional space, but a three-dimensional thing doesn't separate a five-dimensional space. Well, so in more degrees of freedom, with a great deal of effort, Kolmogorov, Arnold, Moser, and many other people have written since this on this, prove the existence of sets of positive measure, for which things remain bounded, on which you have stability. So you have sets of positive measure, but nobody ever succeeded in proving the existence of open sets. Well, that's not quite right. Recently, Michel Herman proved the existence of open sets, but in a rather peculiar situation, which it's a very beautiful result. But it seems to mainly show that the mathematical formulation is too general for physics. Or at least it's too general for the n-body problem.
Open sets of tori. Open sets of tori, which is weird.
Well, what I'm trying to say is open sets on which you have some sort of control on the orbit, so that they don't wander all. You can guarantee that they don't wander all over the space. So you have these orbits on the torus, and they don't wander all over the space. And in this case of 2 degrees of freedom, if you have two tori which are close together, then something in between the tori also doesn't wander all over the space just because it's trapped between the.
High-dimensional version where it still proves bounded orbits. He doesn't have a separation.
Yeah, he has a higher dimensional version, but it has this little tricky point, which means that it doesn't apply to the n-body problem. Actually, it might apply to problems in electrical magnetism. Some expert, actually Herman tries it every so often to get an example with electrical magnetism. But so let me explain what he does. I won't give the proofs. See, there's a basic property that I guess the standard examples from mechanics have, which is that well, we have this symplectic manifold M omega H, and I said that omega is a symplectic structure, so it's a non-degenerate. So omega n does not equal 0, and d omega h equals 0. So if these are the only conditions you want to impose, well, Herman got an example. The observation Herman made right at the beginning when he first produced his examples. Well, in mechanics, one also has that omega is exact. So omega equals dn for some one form. At least that's true in the n-body problem. That seems to be true in every mechanical problem which somebody's ever been interested in. There's some reason to believe that might not be true in every problem in electromagnetics, but that's sort of outside area which I really know anything about. And there's also this remark. It's very easy. It's a remark due to Herman, but it's sort of a key thing in understanding why he can't do what he did when this condition's satisfied. So the remark is that. Oh, I'm sorry. I should warn you that whenever I quote KAM, I manage to leave out some condition. There's so many conditions on the hypothesis, but I left out a condition that Tn is what's called a Lagrangian submanifold. Well, you have the inclusion of Tn into M2n, and the Lagrangian condition is that I star of omega equals 0. So to put this another way, if you have the n torus, and you take two vectors on the n torus and apply omega x to them, you get 0. This is for xy contained in the tangent space of the n torus at some point. Tangent space. I'll put n for tangent space. So this condition is this is one of the hypotheses of the KAM theory. Having said that KAM always has lots of hypotheses, I should also say, you think if a theorem has lots of hypotheses, it might not be very good, because how do you verify the hypotheses? But, well, KAM is a very good theorem because you can very often verify the hypotheses. I guess the basic thing is that in classical mechanics, it's an old tradition to study small perturbations of integrable systems. And if you have small perturbations of integrable systems, at least for a generic integrable system, these conditions are satisfied. Of course, then you observe that all the systems you're really interested in don't satisfy the Kolmogorov condition. So that leads people to write lots more papers on KEM theory, which are very interesting and difficult and technical and so on. But this is yeah, that's the convexity. Right. Let me write down the Kolmogorov condition. Look, the integrable condition is that you can introduce variables. Let me be very brief. You can introduce variables x equals x1 up through xn, which are defined mod 1, and the so-called conjugate variables y1 up through yn, and omega equals sigma dxi wedge dyi. And h is a function of yi alone. h0 is a function of yi alone. So this is your integrable system, and then typically you consider perturbations h equals h0 plus some epsilon of some function, capital H, I guess, of x1 up through xn, y1 up through yn, where the xi's are defined mod 1. This is a very classical problem. I mean, it's studied much in the 19th century by all sorts of mathematicians. And then the basic problem was finally settled in 1960, around 1960, by Kolmogorov, Arnold, Moser. So this is the main. This is sort of the central application of KEM theory. Well, so I wanted to tell you about Hermann's result. So before I tell you about Hermann's result, I follow Hermann's procedure. Hermann's sort of depressive type. So when he tells you his result, first he tells you why it doesn't apply. So I'll follow his procedure. But it's a beautiful result. His result is that if you have a see KAM really is about these tori with linearized vector fields on it. So you might look for more linearized vector fields, which don't necessarily satisfy the Lagrangian condition. This sort of Lagrangian condition comes in a sort of technical way. But Hermann's observation is, well, you take Tn in M2n, and you suppose that it's invariant under xh. And and what else do you suppose? Well, you suppose that it's linearizable. And well, if it's linearizable and one orbit is dense, then every orbit is dense. So assume dense orbits. And then what he says is that, well, the first observation, well, I said it's linearizable, so it has a linear system of coordinates. So let's look at that linear system of coordinates. In the linear system of coordinates, the vector field is constant. So this is, I'll leave as an exercise to you. Let me just say two words. That, I mean, it's constant along the vector field because it's invariant along the vector field. I mean, usually you don't talk about being constant along the vector field because that means you have a particular system of coordinates. But here you do have a particular system of coordinates, so we can talk about being constant. So invariant means it's constant. And the orbit's dense, so since it's constant along this dense orbit, it's just constant. So being constant, well, there are two. If the cohomology class is 0, if the cohomology class of I star omega equals 0, so by this I mean this is, let me be explicit. This is in the de Rham cohomology of the n torus with coefficients in R. If this equals 0, well, if you have a constant 2 form on the n torus, well, if you're a topologist, you know what the cohomology is. In fact, the cohomology is isomorphic to the set of constant 2 forms. The two-dimensional cohomology is isomorphic to the set of constant 2 forms. So, well, if you're a topologist, you'll immediately recognize that the only constant 2 form with 0 cohomology is the 0-2 form. So then I star omega equals 0, which is to say that Tn is Lagrangian. Now, as I remarked, Hermann remarked that in mechanics you have this. It's not just that I star omega is 0, but the cohomology class of omega is 0. So you don't even have to pull back to the torus to get 0. It's already 0 on the whole manifold. So in mechanics, all interesting. Let me put it this way. I put some conditions on the invariant tori, but let me just say, to be very loose about it, call it KAM tori. See, there are all these hypotheses for KAM theory, so I select some set of hypotheses and call it a KM torus. But the exact hypotheses here are the linearizability in the dense orbit. Are Lagrangian. Well, I mean, that's maybe not too a good way to say it. You usually put Lagrangian as one of the conditions to be KM torus. So, well, anyway, you have, so in this 2n-dimensional manifold, if you want to find a torus, it's already n-dimensional. You want to find a torus with a dense orbit, it's already n-dimensional. So let me just put Tn Lagrangian. I'm being very, I'm leaving out some things, but however, if you don't put in this condition, you can find non-Lagrangian tori. In fact, Zender, there are lots of interesting questions about existence of periodic orbits in mechanics, and Zender, at one point, people never believed that every I don't think anybody ever believed that every Hamiltonian system could have a periodic orbit. But there are various conjectures that if you put an extra condition on the manifold, there's the Weinstein conjecture, which I guess is the most famous one, that if you put an extra condition on the manifold, then and you assume that the energy hypersurface is compact, then there's necessarily a periodic orbit. And so after people have been considering this a long time and not being able to prove it, people wonder, so what's the point of the condition anyway? Can you know, let's get an example. Let's get a counterexample without the condition. So Zender provided a counterexample, an example of a on 2 Tn plus 1 cross R with no periodic orbit. Now, Hermann doesn't like this because these examples have the property that, at least if they have dense orbits, well, they have dense orbits. Actually, they have dense orbits in T2n plus. This is minus. Well, it doesn't matter. T2n minus 1. They have dense orbits in T2n minus 1. And so Hermann doesn't like this. But so I didn't prepare this talk well enough. It's very simple to write down, but I don't remember offhand. But what he does is he finds he constructs a symplectic structure on this, which is not the ordinary symplectic structure, but slightly twisted. I'm sorry, I should have prepared this, but I don't remember it at the moment. But the main point I want to say is that omega, the cohomology class of omega is not 0 in the Zender example. Sorry?
You do have compact energy.
Yeah, this is, in fact, the H is the last coordinate. H0. So this is the unperturbed system. This is the unperturbed system which Zender provided Hermann, so to speak. And Zender wrote a preprint and sent it around. And
It's different from what you were considering over here with the linearizable, as far as no dense orbit, no orbit, no closed orbit.
The one thing that's different is that this omega is not 0. So what Hermann did was he remarked, or no, I mean remarked. You have to know Km inside out to make this remark, and he knows it inside out. But he said that if you take the standard KAM method and you impose some further condition on omega, you require that the cohomology class of omega satisfies the Diaphonic condition. Okay, so it's very much like the other Diaphonic condition. Actually, I said Diaphonic condition was a condition on the orbits, so I'm getting sort of tangled up. But the Diaphonic condition can also be thought of as a number theory condition. And if you express it in terms of the number theory condition, you have a number theory condition here, which is much like it. He says that, well, you perturb this system, you keep omega the same, but you perturb H, which is what you always do in this game. And it turns out that the new system, he proved that the new system is C infinity isomorphic to the original system, except you might have to allow a change of time parameter. So this is a remarkable structural stability result. You have C infinity structural stability in this category. That the thing that when you perturb H0, the perturbed thing is just like H0, except for this change of time parameter. In particular, it has no periodic orbits. Well, he got another version of this where then he.
What are the unperturbed dynamics? All the tori have the same irrational.
Yes, they have the same irrational.
They all have the same irrational.
Yeah.
So does Hermann's result require the specific example, or is it mostly just from the over-twisted structure?
Well, he gives the example. I mean, this
Just
is
for that example.
just for that example, but it's basically this. Well, it requires that it be linearizable. And okay, so anyway. No. Yeah, no, certainly not. It's no, in the general case. Yeah, let me say. Well, too many things to say. Yeah, I mean, you may have seen these. If you ever looked at a paper on Hamiltonian systems, you see these pictures of even in the case of 2 degrees of freedom. Well, the case of 2 degrees of freedom is like area-preserving mappings of the plane. And you see these pictures with these curves which the KAM curves which are preserved, And then in between them there are these so-called Birkhoff regions of instability, and there are various other Km curves in that. And then there are stable and unstable manifolds. And this is sort of the generic picture that you have in this mechanics situation. So this comes as if you're used to this mechanics situation, it's certainly a big change from what you're used to, this Hermann thing. And he also produced examples. He also produced examples which are counterexample to this. Well, not to Birkhoff's conjecture. Birkhoff's is about a mechanical system, so he's safe. But to conjecture which people had considered, which is so-called quasi-ergodicity hypothesis of Boltzmann. Any n. Let's see, including 1? Oh, maybe not. That looks wrong for 1. I'm sorry, I think I misspoke. I think I have to start at n equals 2. Yeah, it's surely wrong for n equals 1. In fact, for n equals 1, I have this. I just told you what generally what happens for a generic perturbation for n equals 1. Let's see. No. Oh, no. I'm sorry. That's. Oh, I'm sorry. But these are time independent. So. No. I guess this would be all right. This is trivial for n equals 1. Sorry. Not false. It's trivial. That's why I don't think about it. There's one reason or the other I don't think about it, but I think that it's see in this case you see the energy hypersurfaces themselves are circles, and you just have this vector field which goes around the circle, so it's trivial.
Okay, so the one which should lead to a Km picture, the standard Km picture, should be n equals 2.
Yeah, n equals 2, or you could take a time-dependent vector field of period. To go back to the question you asked me, I guess, if it's time-dependent, then you have this. This is the sort of generic picture that you have.
But I'm having a hard time believing that there actually is a structurally stable area preserving map of the plane to the plane with all filled with invariant curves.
No, it's not a map. It's a vector field. So you have these energy hypersurfaces. You have this energy hypersurfaces. Every energy hypersurface is a circle. I mean, this is the standard remark that Hamiltonian dynamics and time-independent Hamiltonian dynamics in 1 degree of freedom is trivial. It's completely true. I mean, everything is on an energy hypersurface, and energy hypersurface is a circle, and you just keep going around and around the circle. Yeah, I'm running out of time. Yeah, let me just mention that Hermann also constructed counterexamples in this, what he says is excess generality, to 3 other famous conjectures: quasi-ergodicity hypothesis of Boltzmann, which one time people had the ergodicity hypothesis, which is a generic Hamiltonian system is ergodic, and that was disproved by Kolmogorov-Arnold-Moser theory. And then there's Boltzmann's also long time ago. I think mainly because he didn't understand the difference between quasi-ergodicity and ergodicity. He posed the ergodicity hypothesis, which says that generically on an energy hypersurface there's a dense orbit. So for a generic system, on every energy hypersurface there should be a dense orbit. So in 2 degrees of freedom, Moser's KAM disproves that, but in more degrees of freedom, at least that's still open for mechanical systems. But Hermann provides a counterexample to this in the more general class of Hamiltonian systems where you allow omega to satisfy a Diaphonic condition. And in fact, the way he does this is with 2n minus 2-dimensional tori, which remain invariant, and then they're in an energy hypersurface, and again they separate the energy hypersurface. It's very similar. The only difference is that they don't have to be Lagrangian because you have this extra condition, or I mean you drop the conditions. Yeah. So let me just. I have 3 minutes. I wanted to talk a little bit about a conjecture. Well, let me say the conjecture. Say a few words by why I think it's true. The conjecture is that let's replace the planar circular 3-body problem with a planar elliptical 3-body problem. So it's exactly the same as before, except that the 2 bodies with positive mass go around each other in an ellipse. And then again you have this 3rd body. Well, it's again 2 degrees of freedom, but it's no longer time independent. It has a, I mean, I can't, well, you might try, but you won't succeed, I think, unless, well, it would be a great surprise if you succeeded. I don't think you can, see, in the previous case we introduced a rotating coordinate system, and that reduced it to a time-independent system. In this case, as far as anyone knows, there's no analog of the rotating coordinate system which would reduce it to a time-independent system. So now you have a system in 2 degrees of freedom. But time periodic. Not time independent anymore, but time periodic. And you still have these 2-dimensional invariant tori. Trouble is you don't have the 3-dimensional energy hypersurfaces. I mean, you have the T2 contained in the M4, but there's no energy hypersurface in between. So the T2s don't separate the space.
Not an M4 cross R? Or?
No, I think it's just M4, but it's now you have a time-dependent vector field.
You're doing time 1 map?
Well, so yeah, I maybe put R to make the. I mean, you think of usually. Well, yeah, the vector field is the form. Depends not only on the point x, and so in that sense, I guess there's a factor R. So it depends on the point in M and also on a time, and it's periodic in time.
So what happens if you look at the time periodic map? You do have an energy there. You don't have a torus, which is regarding you to the time 1 map?
You have this 2-dimensional torus in M4. Maybe I should put in.
You also have an energy, right? The time 1 map.
Well, the energy hypersurface is not preserved. There's no preserved energy hypersurface, as far as I know. I mean, physicists always write this conservation of energy, dH dt equals partial of h with respect to t. This is nice notation. You have to. is a nice short notation. You have to. It's really hard to understand what it means, though. But I'll try to explain to you what it means. DHDT is, you have the dynamics, so the H preserves under the dynamics, so that's the DHDT. But you also have this H on the manifold, which varies with respect to time. So now you're forgetting about, over here you're forgetting about the dynamics and thinking about the preservation, about just H on this manifold, which depends on time, and this is the derivative with respect to time. So this is the derivative along the orbits, and this is just the derivative in short form. And conservation of energy is that this is equal, which is non-trivial statement. In the case of time independent, it comes down, this is 0, so that's the usual conservation of energy. But now this seems to indicate that the energy hypersurfaces aren't preserved. I mean,
Does the vector field point along the torus?
let's see, I'm maybe getting a little confused here. I guess,
It's really on M4 cross S1.
yeah, I think I should put cross R mod Z or something. Or else, I guess what I was really thinking of was I was taking a, I take a Poincare map, so I continue, I go for one period, and then I come back, and then I have a map of M4 into itself. It's a symplectic map. It's a exacting symplectic map, and this is invariant into that map. That's what I was thinking of.
So how many degrees of freedom does Arnold as a result if you have low enough degrees of freedom the energy remains bounded? So you have a periodically forced Hamiltonian system. And so if you start with a certain amount of energy, you don't have invariant energy surface, but it can't get unbounded.
I don't know this result. We can talk about it afterwards.
Yeah, no. So adiabatically.
Adiabatic is completely different from what I'm talking about. It could be adiabatic.
This isn't adiabatic.
Adiabatic means that it just takes a very long time to become not invariant. I mean, for you to notice that it's not invariant, or that it, it stays for a very long time. It stays in the near the thing. So I'm letting time go to infinity.
That's the whole point of our non-confusion.
For low dimensions, this is above the dimension. This is above, yeah, that's what I was asking, what dimension? Yeah.
So
I think there was a work.
He's just thinking about K, the thing you said, or Km, 2 degrees of freedom to divide, and in this case, no longer divide.
right,
Okay.
right. So let me just make a conjecture that the tori which you construct, well, it's much too brief, but the tori which you construct in this way, my conjecture is that you have orbits which, under, say, as t goes to minus infinity, they approach the tori. And as t goes to plus infinity, they become unbounded. Well, why make this conjecture? I mean, other conjectures are so much more interesting. So the reason to make the conjecture is that I have a method which I think might prove it, but so far I haven't been able to carry it through. The method uses the fact that these tori are action minimizing, and it's a sort of variational method. You try to construct the orbits by minimizing some action subject to some restrictions, and I've done that in other contexts, which I've run out of time, so I can't explain them. But I think this might be a doable problem as opposed to Birkhoff's problem, which I think is far beyond what anybody, well, I don't know. There are all sorts of young guys in the audience who will probably solve it tomorrow, but it's certainly beyond anything I know how to do. So,
Orbits to be dense?
no, I don't expect such orbits to be dense. This is just a substitute for proving things are dense. So, it's much too hard to prove they're dense. So, but well, there are lots of these tori by Km theory. They're almost dense in some sense. So.
Approach the tori. Can you approach any given tori?
Yeah, that's my conjecture, that you can produce any. So I won't tell you about these variational methods. Though they do have one nice property, that they only work when you have this condition. So Herman's counterexamples doesn't discourage you. I guess it encourages you because. Okay. So.